Article 250.32 addresses grounding requirements for separate buildings or structures supplied by a feeder or branch circuit. The core issue revolves around whether to bond the grounded circuit conductor, often the neutral, to the grounding electrode system at the separate building. Understanding the nuances of this article is crucial for ensuring electrical safety and compliance with the National Electrical Code. Article 250.32 done explicitly states that the grounded circuit conductor and the grounding electrode conductor shall not be connected. The purpose of this prohibition is to maintain a clear separation between the grounded circuit and the equipment grounding system, minimizing the risk of unwanted neutral currents flowing through the grounding path. Such currents can create objectionable voltage drops and increase the potential for electrical shock. However, Article 250.32d2 provides an exception to this rule, permitting the bonding of the grounded circuit conductor and the grounding electrode conductor at the service entrance or at the source of a separately derived system. This exception applies specifically when the separate building or structure is served by a new service. The rationale behind this exception is to establish a dedicated equipment grounding system for the building, ensuring that fault currents have a low impedance path back to the source, facilitating the rapid operation of overcurrent protective devices such as circuit breakers or fuses. When a separate building is supplied from an existing service in another building, a different approach is required. In this scenario, the equipment grounding conductor must be run separately from the supply conductors and connected to the grounding electrode system at the separate building. This separate equipment grounding conductor provides the necessary low impedance path for fault currents, while also preventing the objectionable flow of neutral current through the grounding system. This requirement is critical for maintaining the integrity of the equipment grounding system and minimizing the risk of electrical hazards. To clarify these concepts, consider two scenarios. Firstly, imagine a detached garage being supplied with power from the main house. If the garage is considered a separate building and is supplied by a feeder from the main house's service, the equipment grounding conductor must be run with the feeder conductors to the garage. At the garage, this equipment grounding conductor is connected to a grounding electrode system, such as a ground rod or a concrete encased electrode. The neutral conductor, or grounded circuit conductor, must remain isolated from the equipment grounding system at the garage. Secondly, consider a situation where a new service is installed to supply power to a workshop located on the same property as the main house. In this case, Article 250.32d2 permits the bonding of the grounded circuit conductor and the grounding electrode conductor at the workshop service entrance. This bonding establishes a local equipment grounding system for the workshop, ensuring that fault currents have a direct path back to the source. It is important to consult the National Electrical Code for the specific requirements and exceptions related to grounding separate buildings and structures. The NEC provides detailed guidelines for selecting appropriate grounding electrodes, sizing equipment grounding conductors, and ensuring the overall safety and effectiveness of the electrical system. The equipment grounding conductor serves as a critical safety component in an electrical system. It provides a low impedance path for fault current to return to the source, which facilitates the quick operation of overcurrent protective devices like circuit breakers and fuses. This rapid clearing of faults helps to minimize the duration of dangerous touch potentials on equipment and enclosures, thereby reducing the risk of electrical shock hazards. The size of the equipment grounding conductor is determined by NEC Table 250.122, which correlates the size of the overcurrent protective device protecting the circuit with the required size of the equipment grounding conductor. The material of the equipment grounding conductor is typically copper or aluminum, and it can be either solid or stranded. The path of the equipment grounding conductor should be continuous and permanent, providing a reliable connection from the equipment back to the source. Grounding electrodes play a vital role in stabilizing voltage to ground and providing a reference point for the electrical system. Common types of grounding electrodes include ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, also known as UFERs. The selection of the appropriate grounding electrode depends on soil conditions, local codes, and the specific requirements of the installation. Ground rods, typically made of copper or copper-clad steel, are driven into the earth to provide a direct connection to ground. Bran plates, made of copper or other conductive materials, are buried in the earth to provide a larger surface area for grounding. Metal underground water pipes, if in direct contact with the earth for at least 10 feet, can serve as effective grounding electrodes. Concrete encased electrodes, consisting of at least 20 feet of bare copper conductor encased within a concrete foundation or footing, offer excellent grounding performance due to the large contact area with the earth. Bonding refers to the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to safely conduct fault current. Bonding is essential for minimizing voltage differences between metallic parts and providing a low impedance path for fault current to return to the source. Bonding jumpers are used to connect metallic parts together, such as metal enclosures, raceways, and equipment frames. The size of the bonding jumper is determined by a NEC table 250.102 cone, which correlates the size of the service entrance conductors with the required size of the bonding jumper. The material of the bonding jumper is typically copper or aluminum, and it can be either solid or stranded. Proper bonding techniques are critical for ensuring the effectiveness of the equipment grounding system. This includes using appropriate connectors, ensuring clean and tight connections, and avoiding the use of dissimilar metals that can lead to corrosion. The NEC specifies requirements for bonding various components of the electrical system, including service equipment, metal water pipes, gas piping systems, and structural steel. These requirements are designed to minimize the risk of electrical shock and fire hazards. Ground fault circuit interrupters, or GFCIs, are life-saving devices that protect against electrical shock by monitoring the current flowing in a circuit. If a ground fault is detected, the GFCI quickly interrupts the power supply, preventing a dangerous electric shock. GFCIs are required in areas where electrical equipment is likely to come into contact with water, such as bathrooms, kitchens, and outdoor locations. There are two main types of GFCIs: receptacle-type GFCIs, which are installed in place of standard electrical receptacles, and circuit breaker-type GFCIs, which are installed in the electrical panel. Both types of GFCIs provide the same level of protection, but circuit breaker type GFCIs offer the advantage of protecting the entire circuit, including all outlets and devices connected to it. Regular testing of GFCIs is essential to ensure that they are functioning properly. The test button on the GFCI should be pressed monthly to verify that the device is tripping and interrupting the power supply. If the GFCI fails to trip when tested, it should be replaced immediately. Arc fault circuit interrupters, or FCIs, are devices that protect against fires caused by arcing faults in electrical wiring. Arcing faults occur when electricity jumps between conductors or between a conductor and ground, creating intense heat that can ignite nearby combustible materials. FCIs are designed to detect these arcing faults and quickly interrupt the power supply, preventing a fire from starting. FCIs are required in many areas of the home, including bedrooms, living rooms, and dining rooms. There are two main types of FCIs: branch/feeder FCIs, which protect the entire circuit, and combination FCIs, which provide both arc fault and ground fault protection. Like GFCIs, FCIs should be tested regularly to ensure that they are functioning properly. The test button on the FCI should be pressed monthly to verify that the device is tripping and interrupting the power supply. If the FCI fails to trip when tested, it should be replaced immediately. Surge protective devices, or SPDs, are devices that protect electrical equipment from voltage surges caused by lightning strikes, power grid switching, and other transient events. Voltage surges can damage sensitive electronic equipment, such as computers, televisions, and appliances. SPD work by diverting the excess voltage away from the protected equipment, preventing it from reaching damaging levels. There are several types of SPD available, including whole house SPD, which protect the entire electrical system, and point-of-use SPD, which protect individual devices. Whole house SPD are typically installed at the service entrance, while point-of-use SPD are plugged into electrical outlets or connected directly to the equipment being protected. The selection of the appropriate SPD depends on the level of protection required and the type of equipment being protected. Regular inspection and maintenance of SPD are essential to ensure that they are functioning properly. Some SPD have indicator lights that show whether the device is still providing protection. If the indicator light is off, the SPD should be replaced. Electrical panels, also known as load centers or breaker boxes, are the central distribution point for electricity in a building. Electrical panels contain circuit breakers or fuses that protect individual circuits from overloads and short circuits. The electrical panel should be properly sized to accommodate the electrical load of the building. Overloading an electrical panel can lead to overheating, trip circuit breakers, and even fires. The electrical panel should be located in an accessible location and should be kept free from obstructions. All circuit breakers and fuses should be clearly labeled to indicate the circuits they protect. Regular inspection and maintenance of the electrical panel are essential to ensure that it is functioning properly. This includes checking for loose connections, corroded components, and signs of overheating. Any damaged or worn component should be replaced immediately. Wiring methods refer to the various ways in which electrical conductors are installed and protected. Common wiring methods include conduit, cable, and surface raceways. Conduit is a rigid or flexible metal or plastic tubing used to enclose and protect electrical conductors. Conduit provides excellent protection against physical damage and moisture. Cable consists of two or more insulated conductors enclosed in a protective sheath. Common types of cable include non-metallic sheath cable, also known as Romex, and armored cable, also known as BX. Surface raceways are metal or plastic channels used to route and protect electrical conductors on the surface of walls or ceilings. The selection of the appropriate wiring method depends on the application, the environment, and local codes. All wiring installations should be performed in accordance with the National Electrical Code and should be inspected by a qualified electrical inspector. Electrical safety is paramount when working with electricity. Always energize circuits before working on them. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. Never work on electrical equipment in wet or damp conditions. If you are not comfortable working with electricity, hire a qualified electrician. Electrical work can be dangerous, and it is always better to be safe than sorry. Grounding electrode conductors connect the grounding electrode to the equipment grounding system and the grounded conductor, if present, at the service. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the service entrance conductors. The grounding electrode conductor must be continuous and unspliced, unless splicing is permitted by the NEC. Common materials for grounding electrode conductors include copper and aluminum. The grounding electrode conductor should be securely connected to the grounding electrode and the equipment grounding system using approved connectors. The National Electrical Code, or NEC, is a set of standards and guidelines for the safe installation of electrical wiring and equipment. The NEC is updated every 3 years by the National Fire Protection Association, or NFPA. Compliance with the NEC is essential for ensuring the safety of electrical installations. The NEC covers a wide range of topics, including grounding, bonding, wiring methods, overcurrent protection, and equipment installation. The NEC is used by electrical inspectors, contractors, and engineers to ensure that electrical installations are safe and compliant with industry standards. Local codes and regulations may also apply to electrical installations. It is important to consult with local authorities to determine the specific requirements for your area. Understanding and following the National Electrical Code is essential for anyone working with electricity. The NEC provides a comprehensive set of guidelines for the safe installation of electrical wiring and equipment. By following the NEC, you can help to prevent electrical shocks, fires, and other hazards. In summary, navigating Article 250.32 requires careful consideration of the specific installation scenario. Understanding the distinction between bonding at a new service versus running a separate equipment grounding conductor from an existing service is crucial for ensuring electrical safety and code compliance. Consulting the NEC and seeking guidance from qualified electrical professionals are essential steps in ensuring a safe and reliable electrical system.